In this week's video on the EOS models and how they're made, first we're going to take a look at how interparticle forces affect the EOS. We're going to also take a look at the Thunderfalls equation and other equations that look like it. Then we're going to investigate what we mean by a cubic equation of state. And finally, we'll take a sneak peek of what's to come next week. Let's start by adding some interparticle forces. A quick recap. Last week, we set up the assumptions for an ideal system where we said we had a bunch of spheres that were non-interactive. Based on the microscopic variables like velocity, number of particles, and the size of the container, we were able to derive pressure, volume, and temperature, which we used to derive the ideal gas law. If you didn't catch it, make sure to check out the previous video. Adding a slight repulsive and attractive force will change the way the particles behave. Let's look at a simulation where we have a slight repulsive force on the left, no interactive force in the middle, and a slight attractive force on the right, and then compare what happens with the number of collisions with the container. We can see a clear trend that the repulsive force increases the number of collisions, while the attractive force seems to decrease the number of collisions. We could write the total pressure of the system as the sum of the repulsive part of the pressure plus the attractive part of the pressure. Thunderfalls found the repulsive term to be this, and the attractive term to be this. This is in fact the Thunderfalls equation of state. It's interesting to note here that the repulsive term leads to a positive pressure, while the attractive term leads to a negative pressure. This is what we expect from our microscopic model. More recent cubic equation of state have also been developed. One example is the Redlich-Kwong equation of state. Another is the Peng-Robinson equation of state. And we can generalize the cubic equation of state in the following way. Note here that the d term in the denominator has to be a quadratic polynomial. The next thing we want to take a look at is, why do we call it a cubic equation of state? Well, let's show by example, starting with the Thunderfalls equation of state. Putting our algebra hats on, we can do the math together. Oof, that was a lot of algebra, but voila! There we have a cubic equation with respect to the molar volume. We sometimes want to switch out the molar volume for the z factor because it's more convenient to solve for in the equation of state calculations. But the cubic form is still the same. So in the next week's video, we're going to take a look at the cubic equation itself and how it changes with, for example, temperature. We're also going to take a look at how we can use it to actually calculate something useful, like the vapor pressure, and how we can define the critical point of a component based on the cubic equation of state. We'll also take a look at how the volume shift affects the equation of state and the shape of the graph. And with that, I'd just like to say thank you very much for watching, and we'll see you next week. Enjoy the rest of this little teaser animation.